Hello everyone. In this session we will do three simple exercises based on real observations. Till now we assume that we have the precise model at hand, and here we will use measurements to tune our PID controllers. The first one is the most popular Ziegler-Nichols open loop method. What we do here that we set the system in an open loop setup. We use a step excitation. Here in the simulation, we will use unit step excitation. In the measurement, next time when we will have the ping pong balancing exercise, there you can freely choose the step size. So we excite the step, we step this system, and we look at the output, and we will see something like this. And using either this line approximation or other techniques, you have to estimate two parameters. One is the dead time, L. The other is here, the dominant time constant. The line technique is quite simple. So you draw a line on the tangent. Then here you mark the final value. And where it intersects, you draw a line down. You know this time. Then where here it intersects the timeline and the tangent line, here you draw another line. This will be the dead time, and this will be the time constant. And using the finite value and the inputs, you can also calculate the static gain. And based on these three parameters, you can build a simple PID model. For instance, if you want to use a P controller, then you just take these parameters and you divide. Or you can use a PID and so forth. What is important here that this technique works for low order systems, and these are only initial values. So you have to fine tune these values afterwards. Then we have the second Ziegler-Nichols method. This is the closed loop method. Here what you will have to do that you have to put the system in closed loop and set the gain like a P controller. You start with the gain with a value of 1, and you increase or decrease this gain until you see steady state oscillations like this. So you bring your system to the limits of stability. Then you will have two parameters. One is the critical gain, so the gain at the system behaves like this, and you will have this period time, the critical period time, and based on these parameters you can simply make a PID controller or PI or P. Here the problem that not every system can be brought to this stability region. So, and the third one is a little bit manual playing. We have a system 1 over s minus 2. As you can see immediately, this system will be unstable in open loop because our pole is at plus 2. This you can see also in this figure in yellow. Then when I put this system in closed loop, then our pole will move to plus 1, but as you can see in closed loop it's still unstable. Then the idea that here we can use a simple P controller to make this system stable. So in Simulink I use a gadget knob and I can tune this parameter, and as you can see that at this point here 2 plus something, the system becomes stable. And of course you can solve this problem on paper. So here we saw that in closed loop our pole will be plus 1, and we can incorporate this k in our equation. So the what we see here, we have this. From this we see that the pole is k minus 2. So if the pole is a little bit smaller than 0, before build minus 0.001, then it will be stable. So we have to choose k value such that this value will be according to expectation. And what is very nice with this type of exercise, you can read the same information from a body plot as we discussed before. Here are the recommended structures. So in Simulink you can find this PID block, but I ask you not to use it because it's too simple. Then we have this block. Here is the problem, that here we use the discrete time version. In one of my videos I will show you also that this block is really for discrete time simulation. The next best is that you use this simple derivative term. This you can find in the continuous block, but I will explore other possibilities in the list. And here what I recommend to use is this structure. So we use here an ideal D term, and we combine this with a low pass filter in order to limit the noise content. In simulations, you will see no effect because we do not add noise, but with real measurements, you will see a huge difference between the ideal term and this term. Okay, thank you very much for your attention.